So it is a great pleasure to introduce Larry Wasserman. So Larry is the UPMC Professor of Stats and Data Science here at CMU in the Stats and Data Science Department. In addition, he has an affiliation with the CMU Machine Learning Department. And he has been very active with STAMPS, so he's one of the core faculty members of the STAMPS Research Center and has been active with us since the beginning. He's very well known for his many foundational contributions to statistics spanning from theory to methods to applications. And he has gotten many awards for that, including, for example, the Cox Award, which is the most prestigious award in statistics. He was, in addition, elected to the National Academy of Sciences back in 2016. One of the things he's very well known is his textbook on all of statistics. And I think the title really nicely characterizes kind of Larry's activities in statistics, because he's one of the few statisticians who I think are really active in all areas of statistics, and this includes SBI these days. So today, Larry will give us an overview of recent work on SBI at CMU. So please take it over.
Thanks, Mikhail. Thank you for the very generous introduction. Let me also thank Anna and Mikhail for organizing this. This was a lot of work, I know, and it's been going really, really well. I'm very pleased to be able to participate. So my job is to kind of summarize all the SBI stuff that's been going on at CMU, which is a tall task. And let me see if I know how to advance this. Yeah. So I started preparing for this, and I should say I've done a bit of SBI work, but really it's Mikhail and Ann and their students who have done most of it. And so I started looking at all the papers, and this is not even all of them. I can't possibly hope to cover all of that stuff. So I'll try to give kind of highlights from all the stuff there. Again, not complete, but I want to talk also more generally about SBI. And then I've been involved in a couple of these, like it's number 5. This one and number 10 is the one I worked on the most with Lorenzo Tomaselli, who was a former student, and Valerie Ventura, who's a faculty member here. I'll probably bias a little bit towards number 10 just because I'm more familiar with it. But I hope to touch on a lot of these things anyway. And remember, this is my version. Sometimes I'm describing what they did. So, I might not get it 100% right, but I'll try. So I want to do, though, a brief review of, and if I could speak for all of us here, at CMU, how we view SBI at CMU, which is much more typically of a very frequentist framework, and very much like Minge was talking about yesterday about test inversion, and Kyle mentioned test inversion. So I'll do a brief review, though, to establish my notation and how I'm talking about things. Some of it's going to be a little bit repetitive from what we've heard before. Then I will try to summarize some of the stuff going on, and I'll close with open questions. So let me start with this quick review of SBI. And this is, to me, there's 2 different tasks in SBI, and Kyle mentioned this. One of them is estimating the likelihood function, but another one is constructing confidence sets. And they tend to get kind of mushed together here. That's a technical term. They got mushed together. So for example, in ABC, they kind of get done together at the same time. But to me, they're really 2 very different tasks, although obviously related. And I'll try to separate them very clearly here. And the thing about constructing confidence sets, even if the likelihood's tractable, I think SBI is a game changer, because so much of statistics is traditionally relied on you using asymptotic approximations. You're assuming that your model satisfies certain regularity conditions and so on. And there's just so many examples now, especially in complex models, where none of those things apply. And SBI, to me, just completely changes it, because it gives you a way to get exact confidence intervals. And so again, I'm going to focus on frequentist inference. I won't be discussing Bayesian inference. I guess I'm breaking the mold, because today was pretty much all Bayesian stuff. And that means in particular, because in the Bayesian thing, you don't need to do the test inversion step, because Bayesians are lucky; they don't care about coverage. They don't care if it covers 95% of the time, which makes life easy. But if you do want to get coverage for every value of theta, it's a little bit harder. But that's where the test inversion comes. All right. So anyway. The setting is pretty much the same as everybody's been talking about. We have some observed data, y observed, and this could be scalars, vectors, functions, images, whatever. We have some sort of model, which is just a set of distributions indexed by a parameter theta. We want to infer theta, although I know that a lot of times today people talk about uncertainty quantification. To me, that's just what we call statistical inference. And so, again, we're focusing here on the frequentist thing, which means that the probability that the fixed theta is in the random set C is 95% for all theta, no matter what theta is. And that's the hard part in frequentist inference, is that it's the inf over theta, not the average over theta. And of course, I'm following the usual main assumption in SBI, which is that it's easy to simulate from the distribution. So I'm just going to review what, again, Kyle said this, and this is related to how Minga did things, which is constructing a confidence interval by inverting a test. It's very simple, but just to review it, is that for every theta, and this goes back, of course, to Neyman in the 20s or 30s, and the difference is now we can do it at scale. And so for every theta, you want to say, just test the null hypothesis. Is the true value equal to this theta? To do that, we construct a test statistic. It's actually a little bit, it's not quite a test statistic. Well, I guess it is a test. It's an arbitrary statistic depending on y, but it also can depend on theta. And will reject the null if the statistic is big. And the hard thing in frequentist statistics is, what is the rejection threshold? We need to choose this rejection threshold Q so that we exactly get that the probability of rejecting if the null is true is alpha. So getting that quantile or that critical value is the whole game. And then we just invert it. We take all the thetas that were not rejected. And so we teach this to students, in like second year undergraduate, because it follows immediately that gives you a 1 minus alpha confidence set for all theta. And there's two versions of this lead to two slightly different algorithms. One is to concentrate on the p-value, the usual p-value, the probability that if I drew from the model, it would be the test statistic would be larger than the observed test statistic. And then you can rewrite the confidence set as just saying, okay, it's just the set of thetas where the p-value is bigger than alpha. Or you can do it in terms of quantiles. You could try to get the quantiles of the test statistic and choose the 1 minus alpha quantile of the test statistic. And then you can rewrite that confidence set as just the set of thetas such that the observed test statistic is less than that quantile. And what Anne and so on and McCall did, and Kyle's done this too, is using simulation to get the quantile, to get the cutoff, the critical value. That's really the whole game. All right. So to implement that, the way I view it is we were generating theta 1 to theta n from a reference distribution. It's not a prior. You generate typically one data set for each value of theta. We compute this test statistic, and the way I'm writing it is we're generating one data set per theta, but it could be many. And now you create this binary variable. Is the observed test statistic bigger than the one I just created? So now you've got these z's. So now you have a new data set, which is a bunch of thetas and z's, parameter values, and was my test statistic big or not? And now you do a binary regression of z on theta, and that's the p-value. We just regress z on theta, and you are now estimating the p-value for that test, even though you only have one data set per theta. So that's the p-value, and then you just invert it. You just find the set of all theta such that the estimated p-value is bigger than alpha. And I referred to this earlier as an exact confidence interval. but it doesn't look exact because I've got a estimated p-value, because at each data set, I only have one observation. I have to use nearby thetas to estimate the p-value. I'll come back to that point in a minute. Here's a little table just summarizing. Here's the data sets. Here's the test statistics. Here's these binary variables. Here's the binary regression, and there's the confidence set. And here's a picture of it. I'm probably going overboard on explaining all this because everybody's done this, but this is sort of a cartoon. Here's your thetas down here. The dots are your zeros or ones. Was my test statistic in the observed data bigger than the one that I generated? Yes or no? This is the binary regression. We fit a non-parametric regression, and then we chop it off at alpha, and that's our confidence set. The other version, which probably works a bit better, is to emphasize the quantile version. So it's the same procedure: generate the thetas, generate the data, get your test statistics. But now don't bother with the binary thing. Just put together the thetas and the value of the test statistic that you just computed. And now estimate for each theta, you want to estimate the quantile of that distribution at that theta. So that involves, again, a non-parametric regression. We perform quantile regression. We regress the t's on the thetas and estimate the 1 minus alpha quantile. So you estimate this q of theta. And then you just invert that, the set of all thetas, such that the observed test statistic is less than the quantile. I want to say something about how we do this quantile regression. It does not have to be done using neural nets. This is something Barnabosh said this yesterday, is that it's very popular to use neural nets for everything now, which is great because they're very, very effective. But you don't always have to use a neural net. There are other things. A lot of times I see it being done just as a non-parametric regression tool. So for example, to do the non-parametric regression, there's a very easy way to do it is to just do, say, kernel quantile regression, where you put down a kernel, smoothing kernel, and you put down this so-called check function. This is just the loss function that instead of minimizing squared error, if you minimize squared error, you get the mean. If you minimize this loss function, you get the quantile. And so this is very easy to do. It only has a single tuning parameter, a smoothing parameter. Probably takes a billionth of the time that a neural net takes. I just made that up, but it's probably not that inaccurate. And you get more. You get standard errors for the quantile regression. So a little bit of advertising here for non-neural nets. But anyway, once you do that quantile regression, you now have this situation again where you have your data sets, your test statistics, you've estimated the quantile, the 1 minus alpha quantile at each theta, and you invert it. And so the picture is the same, except now you've got, for every theta, you've got a test statistic. This is our non-parametric estimate of the 1 minus alpha quantile at each theta. And then you just chop it off. So the test inversion part is what's going to give you the correct frequentist coverage, but it is a little bit of extra work. It's just, but not that much extra work. You just got to do a quantile regression. One thing that's kind of interesting is, there's different ways of doing this. Some people simulate one data set per theta, but some people simulate several data sets per theta, which would look more like this. And if we imagine you have a fixed budget, that means you're getting more test statistics per theta, but fewer thetas, right? If we have a fixed budget. And I don't think there's been a lot of thought put into which one is better. If you look at the mean squared error of the estimate of your quantile function or p-value function, what happens, roughly speaking, this is a cartoon, but this is roughly what happens, is that if you do one data set per theta, you're spreading out the mean squared error across, it's sort of roughly constant across the whole space. Whereas if you do a lot of replications, where you have replications, you have low mean squared error, but the bias is very big in between. And I'm not sure which one's necessarily the best for constructing confidence sets. So I think there's some design considerations there that deserve some attention. So again, there's no regularity conditions on the model here, which is the really amazing thing. No need to use asymptotic approximations. We are doing a non-parametric regression, either of the p-value function or the quantile function. So, and it's that's sort of asymptotic in the number of thetas we've generated. So when I say it's exact, what I mean is that the coverage of this thing is 1 minus alpha plus an error, but the error is 1 over capital N, which is the number of thetas you simulated, not little n, the number of data points you have. And this, of course, we can take very, very large. So that's what I mean when I say it's exact. I mean, it's not exact, but you can make it as close to exact as you want in modulo computational error, as opposed to traditional statistical things where the accuracy depends on your sample size, which you can't make bigger. You've just got the data. And another thing is that test statistic could be the likelihood function, but it doesn't have to be. And I want to push this point that the likelihood is not necessarily the best thing to be using. In fact, the fact that we can use any test statistic for this gives us incredible freedom. So yeah, this is just this point that this could be the likelihood function, but it doesn't necessarily have to be. And in fact, it can be a way to include, test statistic can include prior information. And I'll mention that Anne and McCall have papers about this, which is a way of kind of getting the best of Bayes and frequentist, because you can put the prior information into the construction of the test statistic, and that allows you to use valuable prior information, but you still get frequentist guarantees at the end. Estimating the likelihood is the other thing. I'll be very quick here because this is the more familiar thing, I think, which is we generate our thetas, we generate our data sets, and then we say permute. These thetas are permuted versions of this, and these are the same data sets, and we create a fake variable which is 1 or 0, and now this is the usual classifier trick that if we now run a classifier on the 1s and 0s, then the probability that y equals 1 given theta and y is proportional to the likelihood. It's really not we call this using a classifier, but you're not really using a classifier. You're using binary regression, because a classifier, all you care about is, was it 1 or 0? Whereas here you really care about what's the probability, but that's a minor point. So a virtue is that you can use any statistic, and when I get to the robust and model misspecification stuff, I'll be showing you things that are not the likelihood based, that are much more robust to model misspecification. And we tend to use the likelihood a lot because, and this is what we kind of brainwash our students in, that the likelihood based things are optimal, but that's a lie, right? They're only optimal under very strict regularity conditions, and it then goes to infinity. And in these complex models, that's far from obvious that there's anything optimal about them. And in particular, likelihood-based things are incredibly sensitive to model misspecification, as opposed to some of the other things we'll talk about this. Okay, and so some of my CMU colleagues here, James and Anne and McCaw, have done things like this, where you take a test statistic, and when we're taking like a ratio of likelihoods, you put a prior in here, but now you use that as the test statistic and you do the test inversion. And so the prior F allows you to focus on certain parts of the parameter space, which can be obviously be very valuable if that's an informative prior distribution. But then when you do the test inversion, we still get the correct frequentist coverage. And you will get smaller confidence intervals as long as the prior is focused near the truth. If the prior is bad, you still get valid coverage. You just won't get the benefit of a smaller confidence interval. And I want to just mention that there's something called FAB, frequentist assisted Bayes, where there's a lot of theory about this kind of thing, about using the prior but getting frequentist coverage. Peter Hoff has quite a few papers about that if you want to read more about that. And in another one of their papers, they do something called Waldo, which again allows you to get the best of both worlds, because they have a prior and they compute the posterior mean, the posterior variance, but then they create like a Wald-like statistic, hence the name. And now that becomes the source of your test statistic, which you now use the SBI with the test inversion. And again, this allows you to include prior information, but preserve frequentist coverage, best of both worlds. Nuisance parameters are Just want to keep an eye on the time. So nuisance parameters, of course, are a big problem. We all know this. I'll talk more about this in the open, when I get to open questions. I have an idea about how to deal with it, one way to help deal with it. But, it's typical that there's a parameter of interest psi and maybe a bunch of nuisance parameters gamma. Of course, you can use the profile likelihood and still do SBI. And you could use the integrated likelihood. What these things or what the profile likelihood really corresponds to is constructing a confidence set by SBI in the whole space and projecting it. And that might not be efficient, but that is a way of getting a valid thing. Mikhail, along with his former student, Mike Stanley, has a paper where they're leveraging something from an old statistics paper by Berger and Blues, which is basically if you have some way of doing some sort of inference first on the nuisance parameter, and you do that at, say, level, for example, 1 minus alpha over 2, you reserve some of your alpha. And now, when you do this projection, you can restrict yourself to a smaller subset of the gammas. You can improve the size of the prediction set while still preserving coverage. So that's an example of how you might modify the typical SBI thing and still get and deal with nuisance parameters. So you might want to look at that paper if you're interested. Another thing that Anne has done a lot is you can always draw new samples from a particular theta and now say, let's pretend that's the truth. And then we run our whole SBI thing, and then we can check the coverage of that particular theta, and you can do that for all the thetas. And so the nice thing about all of our software is they have these diagnostics that say, not only is this providing you with this theoretical guarantee, but you can check it and see actually how well is it covering. And by the way, you can also use this to compare. You could have several different statistics. You could compare them by nominating different thetas to be the truth and say which one gives you the smallest confidence set, for example. So this can also help choose between different test statistics. So we had a nice talk about spatial statistics yesterday. I want to highlight a paper by Mikhail and his student Julia. Julia was here before. Oh, there's Julia. I'm not at all an expert on these things, but I know that they were very successful at getting these spatial models can have, intractable likelihood functions. And actually, we heard about that in the previous talk too. So typically you have this process now where S's are different locations. I know in their paper, they consider a Gaussian process because you can check your answer, but even Gaussian processes can be expensive. And then they also considered this Brown-Resnick process, which I think is related to some of the extreme value processes that were spoken about. But again, I'm not an expert on spatial things, but this is apparently a well-known, intractable kind of a thing. And so what they SBI-ified it. And, I would, again, invite you to look at the paper, but I wanted to show you the results, which I think are kind of amazing. Because remember, in this frequentist approach, you want to make sure, am I getting 95% coverage for every point in the parameter space, no matter what theta is? And what this picture I stole from their paper is first of all, this is a competing method, a different method. And what we're showing here is two parameters. This is the parameter space. And the color is how well is it covering? How often are you actually covering the truth? And if it's 95%, it should be like yellow. And so you can see this previous method does not do such a great thing. Here's another version of that, which is doing better here, but it's screwing up, around the edges here. And then this is what Mikhail and Julia did. And here's two versions of their thing. And the second one is just making a point I made earlier, which is not only are they doing a classifier, but then they calibrate it, as you often do. And the reason why you need to calibrate it, of course, is because you're not just trying to predict ones and zeros. You're trying to actually get what's the probability that W equals 1 given theta. And you can see the difference that makes. But look how well it covers. I mean, the entire space just nails it. So I think that's really cool. And they have a follow-up paper, which I'll describe even less, because I don't know about so much, but they want to also not just do inference, but simulate new observations. So you want to draw a new observation from the spatial process once you've estimated the parameters. The technique they're using is what Barnabosh spoke about yesterday, diffusion processes. But this is a kind of unusual use of diffusion processes because mostly they've been used, as Barnabosh described yesterday, that you take a bunch of images, you add noise to get Gaussians, and then you try to go backwards and generate new images. Here they're doing it for scientific reasons. So they have their data, they somehow evolve that to be noise. I can't tell you the details, and they do manage to reverse the process even in the spatial setting. And so they can evolve that backwards, and now they can not only do inference for the parameters, but they can sample new observations. I just put the standard diffusion picture here that everybody puts up, a cat turned into noise and backwards. That's not what they're doing, but that's what, when I went on the web and typed diffusion process, that's what I got. Another area where these things are used, this is, again, that Mikhail did with some students about inverse problems, which come up, of course, all the time in physics, where you've got, here's one version, y is f of x plus epsilon. You don't know x, it's high dimensional. And the case they deal with is you have all these constraints on x. And you want to infer not x, the thing you didn't observe, but some functional of x, phi of x. And again, the game is, though, you want to be very strict about making sure that the probability that you cover this is 1 minus alpha, no matter what x is. And the interesting thing here is, I'm not going to, again, go into details, but there was 2 versions of this paper, as I understand it, and the second one had a great improvement, and Mikhail can correct me if I'm wrong, because they were able to simulate the quantiles. And so the simulation came in here into very carefully getting the appropriate quantiles. Just to give you an idea, it's kind of complicated. This is a picture I stole from their paper where you've got this x trapped in this unknown set. You've got a functional of interest. There's a forward model here. And so there's a lot going on here. And they've been able to advance this. And of course, this is a problem that comes up all the time. Another inverse problem approach is due to Ben Nachman and his students, and we have a paper actually with Ben that's just finished or finishing. I forget where we are in this, which is very cool, and it's using SBI to do a general inverse problem. Okay, so the idea is kind of a standard inverse thing called, I guess it's called unfolding in physics, which is you have a sample from a density, P of y, but P of y is actually K of y given x averaged over f of x. We don't see the x's. And so you're trying to recover this function f of x. So kind of a standard inverse problem. But there's two extra things here. Usually you take this kernel K to be known. Here, the kernel is unknown. And you have a secondary sample, which I've indicated with the stars, drawn. The density for X is a different density, but the kernel is still the same. So you have less information because you don't know the kernel, but you have more information because you have this extra sample. So there's this simulation part of it. And you want to infer either f of X, or if you want to think of it this way, as a density ratio, as we'd like to think about in SBI, the ratio between F and this reference density R. And it turns out the solution that Ben came up with is a kind of an SBI version of something that already existed. There's a solution that goes all the way back to, I think we traced it to 1987, which is just basically, this is a freedom equation of the first kind, and there's these iterative methods for solving those equations. It looks like this, that you have a previous thing, you can estimate P of y, and you do this integral essentially, and then you iterate this. And what this thing is, omnifold, is basically an SBI version of this. And So they invented a simulation-based version. The steps are quite simple, but the key thing to notice is that you keep having to get these density ratios. Well, we know how to do that, right? That's SBI. So the SBI version allows you to get these density ratios, and now you iterate, and this will convert under some conditions, will converge to the estimate. So they can be estimated using classifiers. And we have this paper about adding nuisance parameters to this problem. All right, now I want to turn to my paper with Lorenzo and Valerie, and which focused on model specification. I should have put the archive link here, sorry about that, but this is on archive. So again, we have a model, but now we want to make the assumption that the true distribution is not in there. So I'm not going to use the George Box quote. I'm going to use the Tukey quote instead. Fewer people know the Tukey quote. The Tukey quote is, use models, but don't believe them. Okay, we're going to use the model, but we're not going to believe it. So the way we're going to proceed is we're going to choose a discrepancy, D, which is just a distance between distributions. And what is it what are we inferring actually? Well, we're going to define the target of inference to be what I call the projection parameter. Somebody else, I think Minga called it the oracle parameters also. That's a good name too. Which is just the value of theta that minimizes the distance between the true distribution and the guy in your model. And so that's going to be our target of inference. So we're kind of acknowledging explicitly, the model is just an approximation, and I'm going to try to target the closest element in the model to the true distribution, which is a much more honest way of doing inference, if we want to think about it that way. But which discrepancies should you use? So I think Andrew mentioned yesterday, I think it was Andrew, said that, well, when you're doing maximum likelihood or Bayes with a misspecified model, you're implicitly minimizing the Kullback-Leibler distance. You're trying to find the thing closest in Kullback-Leibler distance. But actually, when the model is, and so that's what that statement says, but this is an extremely non-robust thing to do. The Kullback-Leibler distance is famously non-robust. An example would be, let's just take a normal with probability 1 minus epsilon. Epsilon is going to be tiny, tiny, tiny. Plus epsilon times QA. QA will be some distribution centered at a point A, very far away. Epsilon is going to be very, very small. What is the projection? What is the closest normal? Well, the closest normal will be a normal with some mean mu that depends on A. And the thing is, as A goes to infinity, that mean goes to infinity. So even though my distribution looks identical to a normal, you can't even tell the difference by looking. I've got a tiny bit of mass out there. When I do the projection as my model, it's going to be over here. So it's going to look like this. The black model is the normal, and there's a tiny bit of mass out there. The red distribution is what you're estimating if you use maximum likelihood or Bayes. That's the Kullback-Leibler projection. I'll talk about better projections that are much closer, like the blue one. So here you go. One discrepancy. So in our paper, we considered 3 different discrepancies and studied how well the 3 different discrepancies work and so on. One that's goes back to the 70s in statistics is called the Hellinger distance, which is just the L2 distance between the square roots of the 2 densities. But this turns out to be an extremely special. So this one's very special. It's got lots of interesting properties. Another one that gets used a lot in the statistics literature, I haven't seen it in other places so much, is called the density power divergence. The formula is a little bit of a mess, but it turns out to be very easy to work with. And it's got this parameter gamma, which has a very nice interpretation. As gamma goes to 0, it becomes the Kullback-Leibler distance, and so you're doing maximum likelihood. And as gamma goes to 1, it becomes the L2 distance, which we all know and understand well, and that's much less. So what gamma does is it trades off efficiency and robustness. And I think one of the things that no one's done yet is in SBI, I think you can try to choose an optimal gamma, but I won't have time to talk about that. But gamma trades off efficiency and robustness. I think this idea of trading off efficiency and robustness is something that's really hard to do in traditional statistics and becomes quite feasible in SBI. Another distance we looked into is kernel distance, or sometimes called MMD, maximum mean discrepancy. It looks like this. You choose a kernel, and here x and x prime are drawn from P, and y prime are drawn from Q. That's just another distance. It has all kinds of nice properties. It's equivalent to taking the maximum difference between the mean under x, under P and under Q, where F varies over this reproducing kernel Hilbert space. Okay, so which discrepancy should you use? So in our paper, we look at all these things. Unfortunately, I don't have a super good answer because there's, as you might expect, they have advantages and disadvantages, right? So in terms of robustness, the KL distance is very non-robust. Hellinger, the DPD, and the kernel are all very robust. So that's good. By efficiency, what I mean is, suppose you're lucky and your model's correct. Are you getting the most efficient estimator, the one with the smallest variance? Well, KL, yes, because it's maximum likelihood or Bayes. Hellinger, yes. Hellinger is one of the few discrepancies which has the property that it's simultaneously robust, but it's efficient if the model's true. That's why it's a special distance. And there's a whole set of papers in statistics called minimum Hellinger estimation because of this. The DPD is not quite efficient, nor is the kernel. These ones have the unfortunate thing that you do have to estimate a density or a density ratio, whereas the kernel distance, actually, you never have to estimate any densities. And unfortunately, the kernel one, though, you have to choose the kernel, which is a big tuning parameter you have to pick, and it really matters how you pick it. So they all have advantages and disadvantages. How do you do inference now? Okay. So remember, the projection parameter is this minimum distance thing, but I want a confidence interval for that. You cannot invert a test to do that. If you test for when you're inverting a test, you're taking every theta and say, is this the true theta? Is this the true theta? Is this the true theta? The answer is none of them are, because the model's wrong. And what will happen is a very weird thing. As you get more and more data, the confidence set gets smaller and smaller and smaller because it's discovering these models are not correct, and eventually your confidence set would be empty. But actually, the worst case is when it's not quite empty. You're going to get a small confidence set. Think, wow, I'm really estimating this really well, but that's just because the model doesn't fit. So you can't invert to get confidence sets in this case. So what do we do? Just to be concrete, I'm going to use the DPD distance with gamma equals 1. That is the L2 distance, which is just this. So first of all, we have to estimate this distance. That's where the SBI comes in. So it turns out you need yet another sample. So you have the data, you have your samples from the model, and now you need another sample from a reference distribution. It just turns out this is what you have to do. There's a bunch of density ratios going on now. There's P of theta, there's P, there's the reference density. We estimate all those, we know how to do that now. We're all experts. And if you do that properly, this should have been like, this psi here is actually this thing. The point is, there's a very simple formula now for the estimate of the altitude distance or any of those other distances. You do have to estimate, though, these ratios, but again, we're doing that anyway for SBI. Running out of time here. Okay, so to get the confidence set, if you look up the literature on minimum discrepancy, they'll give you a formula for the confidence set in terms of a chi-squared, and in terms of this thing here, which is known as the sandwich formula. This is the bread, B, and M is the meat, M. But that formula is no good because it's relying on regularity conditions and asymptotics, and we don't want to do that. And so what we do is, this is something a few of us at CMU, these are all CMU papers actually. Here's a way to do it. One way to do it. You would have to split the data. So we're hoping you have a bit of data, although there's a way to get around the splitting. But let's say you split the data, and from half the data, you get a preliminary estimator, like running this whole procedure. And then instead of testing is theta the true parameter, you test this. You test, is the distance between P and your theta smaller than the distance between P and your initial estimator? And the difference of those distances is just some sum. I put it up on the other page. And here's the really crucial fact. This is just a sum. So the central limit theorem applies, and this is approximately normal. And I said, but I don't want to rely on asymptotics and regularity conditions. This does not require regularity conditions of the model. This is just saying that a sum is asymptotically normal. It's a very, very important distinction, that the model can be horrible. It can be not even identified, and yet this will still be true. In fact, I've done, and I won't talk about it here, but I've done a bit of work on, or quite a bit of work on applying SBI to epidemic models. And this is what happens is at the beginning of the epidemic, the parameters are not well identified, but this still works. So this is approximately normal without any regularity conditions. And so we know what to do with the normal. I'm just basically testing whether the mean of t is 0 or bigger than 0. And so I just reject that if it's big, I invert that. And now you have a confidence interval for the projection of the model. Okay. And that will have the right coverage. So a typical example, everybody sort of uses this example for SBI, that it's kind of a, benchmark. You have a mixture of normals. This is not even identified, right? If mu1 equals mu2, you can't estimate lambda. If lambda is 0, you can't estimate mu2. Every regularity condition known to mankind fails. Standard methods don't work. If you run this procedure I just said, though, you get these beautiful results because we're doing a case here where the model's not correct. I think the model's not correct here, but the projection is a single normal. So mu1 and mu2 are not separately identified. And the confidence set tells you that. It's showing you, oh, it could be that mu2 is 0 and mu1 is here, or it could be the other way around. We can't tell. You'll never get a confidence set of this shape, of course, from standard chi-squared things or things like that. All right. How am I doing? I have 3 minutes.
Yeah, but if I think you're taking the time to do this slide. So,
well, okay, I'll go fast. Kyle flashed up yesterday a picture of this. Is that another way we looked at for getting robustness is by tilting, where you choose some basis functions and you just enlarge the model. But importantly, so P theta is our original model. We don't actually maybe know P theta y, but theoretically we're taking this and we just take e to a sum of beta j times b's. This is called an exponential tilt. And of all the ways to expand a model, the idea here is if you expand the model, it's got a better chance of being a pretty approximately accurate model. But doing an exponential tilt has all kinds of advantages when you're doing SBI, because now I've got all these extra nuisance parameters, these betas, and I want to get rid of them. But for a fixed value of theta, if I fix theta, this is as a function of beta, it's not one of these complicated models. It's just a very simple exponential model. So inference is very simple for this. So we've introduced nuisance parameters, but in a way that ensures that we can do it very quickly and get confidence intervals, and you can use Newton-Raphson. So maybe I should, I'm going to probably go to this is another thing you can do. I'm going to skip this. You can also, when you're doing these things, get a closed form approximation to your interactive model using similar techniques. Okay, so I'm not going to go through that. I had a little bit about active learning. I just want to say in active learning, the key thing is what we really want is the boundaries of the confidence set. So we have something in our paper about targeting the boundary of the confidence set. That's really what you want to estimate properly. And I'm going to skip this too. You can also, once you have all these things going, you can do goodness of fit testing. And again, that's not trivial because most goodness of fit tests for a model rely very heavily on asymptotics. And we don't want to do that. It turns out to get SBI to do the goodness of fit test is a little bit more complicated than doing inference. But we were able to, you can certainly get it to work. So what I really want to do is get to my closing, which is open questions and challenges. So I think everybody agrees that high dimensional parameter spaces are a big challenge. When I think about well, first of all, there's generating the data. That's a bottleneck, but let's assume you can generate a lot of thetas and generate a lot of data. What is the bottleneck after that? It's not getting these quantiles or these p-values because, quantile regression, we have ways of doing that. For example, we have quantile regression forests and so on, or for that matter, neural nets. You can do quantile regression in high dimensions. I think the hard part is finding the confidence set. You're sampling all over the place and you're looking, for this thing over here. So to me, I think one of the most important things is active learning, which is to sample sequentially and to try to narrow down where the confidence set is. And I think we all agree that's important, and that's also very hard to do. But here's something else that going back to nuisance parameters. It would be great if since we have the choice of choosing any test statistic we want, wouldn't it be great if we had a test statistic whose distribution was very insensitive to the nuisance parameters? That would make our lives much easier. It would mean that if you screw up about where to sample in the nuisance space, it doesn't matter as much. And again, the likelihood is not necessarily the best thing for this. In fact, it's not. Now, do we have methods, sort of traditional methods in statistics for doing this? We do. You take the score function. So suppose you have a parameter of interest psi, and then you have a bunch of nuisance parameters. You compute the score function, the derivative of the log of p with respect to psi. You compute the score with respect to all the nuisance parameters. And now you create a new statistic by taking the score for the parameter of interest minus its projection on those other score functions. That's kind of a well-known thing with statistics. That reduces the sensitivity to the nuisance parameters. But then, how do you do that in SBI? Well, from listening to everybody talk, I was thinking of getting those derivatives is hard, but I guess not, right? That's one of the good things about neural nets. I don't know how to run neural nets, but you get out derivatives too. So that means you can get out the score functions, and you could potentially do this. So I think and that's just one, I'm just throwing out a random idea there, but I think that's something in principle one could do to get a new test statistic, which is less sensitive to the nuisance parameter. And which is part of course, the big question, which is how to choose T. And I know we all love the likelihood, but it's not the only thing out there. And I really think in complicated problems, it's often not the best thing to be doing. The last thing I want to say, and Kyle mentioned this briefly, semi-parametric and non-parametric inference. I mean, semi-parametric inference is when we have, a parameter of interest, which is Euclidean, and we have nuisance functions, not just nuisance parameters, but nuisance functions. In statistics, we have a lot of theory for doing that, but they're not amenable to SBI. And so I think it'd be really interesting to try to figure out how to do that. And then, of course, there's just non-parametric things when you don't even have just parameters. And so getting SBI to work in this larger class of problems, I think would be very, very interesting. That's it. Thanks for your attention.